Module 2, Limits and Rates of Change, Part 4. Let's revisit the mathematical machinery we introduced in Part 3. The instantaneous rate of change in a function f at x equal a is given by f prime of a equals the limit as delta x approaches 0 of f of a plus delta x minus f of a all over delta x. This equation is referred to as the limit definition of the derivative, and the instantaneous rate of change itself is called the derivative. So when you hear the term the derivative, you should think in your mind instantaneous rate of change. Let's remind ourselves graphically what we're even talking about here. So over on the right, we have the red graph. That represents the graph of f. And I've denoted 2 points on that graph, the point a, f of a, and the point a plus delta x, f of a plus delta x. Those are the 2 points I've denoted on that graph. And then I've drawn the calculus triangle defined by those 2 points. Notice the base of the calculus triangle is delta x. That's the distance between a and a plus delta x. And then the vertical component of that calculus triangle is f of a plus delta x minus f of a. Again, that's just the difference of the y values. So what we're really looking at is y2 minus y1 for the vertical component, the green component, and then x2 minus x1 for the horizontal component, which is the blue component. The purple line there represents the slope of that line represents the change, if you will, in the output divided by the change of the input. So that shows the steepness, if you will, and that's defined by our calculus triangle. We're going to build on this idea and apply a lot of algebra to try to make sense of this with a variety of different functions. So pause and go to your notes, and in your notes to your future forgetful self, explain the meaning of each component of the instantaneous rate of change formula for a function. Again, the instantaneous rate of change in a function f at x equal a is given by f prime of a equals the limit as delta x approaches 0 of f of a plus delta x minus f of a all over delta x. In your notes, you should make sure you know what f prime of a represents, what the limit as delta x approaches 0 means, what delta x means, what f of a plus delta x means, what f of a means, and what all the components together, what those mean. A solid understanding of this formula and the components of the formula will greatly enhance your ability to be successful moving forward. All right, let's dive into another learning task. For each of the following functions, use the limit definition of the derivative to represent the instantaneous rate of change in the function at the value of x equals 3. At this stage, you do not need to simplify the function algebraically. You're simply going to be plugging in the value of 3 for a, and then applying the limit definition of the derivative, just doing the substitution and stopping. Go ahead and pause the video and stop and work these problems. All right, let's walk through these one by one. We know the instantaneous rate of change in a function f at x equals 3 is given by this equation. F prime of 3 equals the limit as delta x approaches 0 of f of 3 plus delta x minus f of 3 all over delta x. Now there's a lot going on there in that definition of the derivative, and so it's often very helpful to go off to the side and figure out the individual components and then come back into the main flow with those components. So you can see here, I go off to the side. I know my function was defined as f of x equals x squared. I need to find f of 3 plus delta x. Well, just substituting in 3 plus delta x where there was an x, I can see that f of 3 plus delta x equals the quantity 3 plus delta x quantity squared. For f of 3, I simply replace the x with a 3, and I see f of 3 equals 3 squared. And so I plug in those component pieces. And again, for this part of the process, we can just stop there. What I'm trying to help you develop right here is this ability to use function notation and move from the limit definition of the derivative itself to apply that for a specific function. And so we'll continue these later on, but for right now, this will be the first step. Let's move to the next function. We have the instantaneous rate of change in a function g at x equals 3 is given by, and we see the limit definition of the derivative, evaluating this function at 3. Again, we move off to the side. We see the definition of g. G of x was defined as 4x plus 5. We evaluate that function at two values, the first one being 3 plus delta x. Again, we just replace the x with 3 plus delta x. And also, we evaluated it at 3. So g of 3, we just replace the x with a 3. We then import those components into our limit definition of the derivative. And we stop there for right now. We'll continue on later. Let's look at the next function. The instantaneous rate of change in a function h at x equals 3 is given by h prime of 3 equals the limit as delta x approaches 0 of h of 3 plus delta x minus h of 3 all over delta x. Again, we go off to the side. Now h of x was defined as 6. So h of 3 plus delta x will be 6, h of 3 will be 6, h of anything is going to be 6. We import those values into the numerator, 6 minus 6, and we stop. Again, we're just testing or practicing here our ability to use function notation and then make those substitutions into the limit definition of the derivative. All right, let's look at the function j. The instantaneous rate of change in a function j at x equals 3 is given by j prime of 3 equals the limit as delta x approaches 0 of j of 3 plus delta x minus j of 3 all over delta x. Again, we go off to the side. We know j of x was defined as 2 to the x. We evaluate that function at 3 plus delta x. That is, the x in the exponent becomes 3 plus delta x. And then we evaluate it for j of 3, and we get 2 cubed. And again, we import those values into our limit definition of the derivative. The purpose of these last four problems was to, again, familiarize you with function notation and to kind of establish this routine, this methodology for approaching solving problems with the limit definition of the derivative. We are now in learning task 8 going to extend that process. So you've already done the setup on all of these. Now we are just going to continue on and solve each problem until we have a value for the instantaneous rate of change. And so we will go ahead and pause the video here and continue each of those problems that you started before and work them to the end until you end up with a numeric value. All right, let's revisit the first problem. The instantaneous rate of change in a function f at x equals 3 is given by, we have the side computations that we generated before, and then we just import those into our function. And you can see that I did that there on the left-hand side. At about step 3 is where I import those values. And we see that we have 9 plus 6 delta x plus delta x squared minus 9. Those two 9s in the numerators cancel out, leaving us with 6 delta x plus delta x quantity squared. But we're dividing that numerator by delta x. It goes in evenly to both of those terms in the numerator. So we end up with f prime of 3 equals the limit as delta x approaches 0 of 6 plus delta x. Now let's think about this. That delta x value is getting closer and closer and closer to 0. Matter of fact, we can get as close to 0 as we want. And as we do, the value 6 plus delta x gets closer and closer and closer to 6. So f prime of 3 equals 6. Or in other words, the instantaneous rate of change in the function f, which was defined as x squared, at the value of 3, again, that would be our input value, is 6. And it would be 6 units squared of output per unit of input. All right, now let's look at the function g. Again, we've done some preliminary work on that, which we see off on our side computations. We come back over to the main flow. We've got g prime of 3 equals the limit as delta x approaches 0 of the quantity 17 plus 4 delta x minus 17, all over delta x. The 17s cancel out, leaving us with 4 delta x over delta x. The delta x can be canceled. We get the limit as delta x approaches 0 of 4. Well, notice that term doesn't have a delta x in it at all. It's just the value. So the limit must be 4. So g prime of 3 equals 4. In other words, the instantaneous rate of change in the function g of x equals 4x plus 5 at the value of x equal 3 is 4 units per unit, and 4 units of output per unit of input. Notice this is actually obvious to us. The function g of x equal 4x plus 5 is a line with a slope of 4, and the instantaneous rate of change is in fact the slope of that line. And so there's no surprise there that our answer of g prime of 3 equal 4 matches the slope of the line. Now let's move on to function h. Again, we've got side computations for function h. We know that the output value is always 6. It never changes. So when we substitute those values in, we get h prime of 3 equals the limit as delta x approaches 0 of 6 minus 6 all over delta x. But 6 minus 6 is 0. So the limit of delta x approaching 0 of 0, again, there's no delta x left over, so this must mean it's 0. That is, the instantaneous rate of change of h at x equal 3 is equal to 0 units vertically per unit horizontally, or unit of output per unit of input. There is no change here, and that's no surprise. Again, this is a constant function, and we know that the output doesn't change. And so that's what it tells us here. Each 1 unit of output, of input, does not result in any change in the output. All right, let's move on to function j. The instantaneous rate of change in a function j at x equal 3 is given by, and again, we have our side computations from earlier. We bring those values in. So we've got j prime of 3 equals the limit as delta x approaches 0 of 2 to the 3 plus delta x minus 2 cubed all over delta x. We did simplify that a little bit on the right, so I'll go and move to that step. J prime of 3 equals the limit as delta x approaches 0 of 8 times 2 to the delta x minus 8 all over delta x. We can factor out an 8 in the numerator, so we've got j prime of 3 equals the limit as delta x approaches 0 of 8 times the quantity 2 to the delta x minus 1 all over delta x. And because the delta x does not impact that 8 in any way, we just move the 8 in front of the limit. So we have j prime of 3 equals 8 times the limit of delta x as delta x approaches 0 of 2 to the delta x minus 1 all over delta x. Well, now we have a conundrum. We do not know how to algebraically simplify that expression, 2 to the delta x minus 1 all over delta x. But we remember that delta x represents a small horizontal change, right? A small change in the input. And so we're going to numerically estimate that value by choosing a very small change in the input. We'll continue that on to the next slide. So over on the right-hand side, I've constructed a table. And on the left-hand side of the table, we have delta x, and we're going to evaluate this function at a variety of values. On the right-hand side, I have that limit. And again, I'm looking at that, specifically that quantity, 2 to the delta x minus 1 all over delta x, and is what I'm looking at. We should have ignored the limit there on that piece. I should have not included that on the slides. My apologies. The limit as delta x approaches 0. Just block that out in your mind. We're really focusing just on that ratio. So as we evaluate this at varying values of delta x, you can see it's approaching about 0.6931. So over on the left, where I have that limit expression, I simply replace that with 0.6931, and I get an approximation of 5.5448. In other words, this original function, which was 2 to the x, at x equals 3, has an instantaneous rate of change of 5.5448 units of output per unit of input. All right, that was some heavy lifting right there. So go ahead in your notes to your future forgetful self. Discuss the problem-solving strategies used in finding the instantaneous rate of change of a function using the limit definition of the derivative, which I've shown there below. Again, think about the strategy that was used in the problem solving, perhaps some challenges you encountered along the way. This is to give yourself tips on how to successfully navigate these problems.